Hello everyone, my name is Ajay Medji from Aeronautical Engineering. In this presentation, I am going to discuss about my tech talk topic is liquid propellant rocket. Abstract. A liquid propellant rocket or liquid rocket utilizes a rocket engine that uses liquid propellants. Liquids are desirable because they have a reasonable high density and high specific impulse. This allows the volume of the propellant tanks to be relatively low. It is also possible to use lightweight centrifugal turbopumps to pump the rocket propellant from the tank into the combustion chamber, which means that the propellant can be kept at under low pressure. This permits the use of low mass propellant tanks that do not need to resist the high pressure needed to store significant amounts of gases, resulting in a low mass ratio for the rocket. An inert gas stored in a tank at high pressure is sometimes used instead of pumps in simpler small engine to force propellant into combustion chamber. In this diagram it is showing the liquid propellant system in a rocket. The first one is like oxidizer, and the blue one is the first one is fuel and the second one is oxidizer. After mixing of this fuel and oxidizer, the combustion starts in green tanks. After that, the high pressure and temperature gas is leaved from the combustion chamber to the nozzle, and nozzle allows us to, it will increase the acceleration of the flow, and the thrust is generated in the nozzle. These engines may have a higher mass ratio but are usually more reliable and therefore used widely in satellites for orbit maintenance. Liquid rockets can be monopropellant rockets using a single type of propellant or bipropellant rockets using two types of propellant. Tripropellant rockets using three types of propellant are rare. Some designs are throttleable for variable thrust operation, and some may be restarted after a previous in-space shutdown. Tripropellant rockets using three types of propellant are rare. Some designs are throttleable for variable thrust operation, and some may be restarted after a previous in-space shutdown. Liquid propellants are also used in hybrid rockets with some of the advantages of a solid rocket. Here in this, the pictures are showing the liquid propellant rocket. The left side is the rocket principle of operation. All liquid rockets have tankage and pipes to store and transfer propellant, an injector system, a combustion chamber which is very typically cylindrical, and one rocket nozzles. Liquid systems enable higher specific impulse than solids and hybrid rocket motors and can provide very high tankage efficiency. Unlike gases, a typical liquid propellant has a density similar to water, approximately 0.7 to 1.4 gram per centimeter cube, except liquid hydrogen, which has a much lower density while requiring only relatively modest pressure to prevent vaporization. This combination of density and low pressure permits very lightweight tankage, approximately 1% of the contents of dense propellant, around 10% for liquid hydrogen. For injection into the combustion chamber, the propellant pressure at the injectors need to be greater than the chamber pressure. This can be achieved with a pump. Suitable pumps usually use centrifugal turbopumps due to their high power and lightweight, although reciprocating pumps have been employed in the past. In this slide, liquid propellant engine. The maroon color is fuel, the blue color is oxidizer. When the fuel and oxidizer mix together in the combustion chamber, it will generate high amount of pressure and temperature. It leaves towards the nozzle and the thrust is generated. Here is thrust equation. F is equal to mass flow rate m dot VE plus PE minus P naught into AE. The thrust equation is both same for solid and liquid rocket engines. On this slide we show a schematic of a liquid rocket engine. Liquid rocket engines are used to place humans in orbit, on many unmanned missiles, to place satellites in orbit, and on several high-speed research aircraft following World War II. In a liquid rocket, stored fuel and stored oxidizer are pumped into a combustion chamber where they are mixed and burnt. The combustion produces great amount of exhaust gas at high temperature and pressure. The hot exhaust is passed through a nozzle which accelerates the flow. Thrust is produced according to the Newton's third law of motion. The amount of thrust produced by the rocket depends on the mass flow rate through the engine, the exit velocity of the exhaust, and the pressure at the nozzle exit. All of these variables depend on the design of the nozzle. The smallest cross-section area of the nozzle is called the throat of the nozzle. The hot exhaust flow is choked at the throat, which means that the Mach number is equal to 1 in the throat, and the mass flow rate m dot is determined by the throat area. The area ratio from the throat to the exit AE sets the exit velocity VE and exit pressure VE. The exit pressure is only equal to free stream pressure at some design condition. We must therefore use the longer version of the generalized thrust equation to describe the thrust of the system. If the free stream pressure is given by P naught, the thrust F equation becomes F is equal to m dot into VE plus PE minus P naught into AE. Notice that there is no free stream mass times free stream velocity terms in the thrust equation because no external air is brought on board, since the oxidizer is carried on board the rocket. Rockets can generate thrust in a vacuum where there is no other source of oxygen. That's why a rocket will work in space where there is no surrounding air, and a gas turbine or propeller will not work. Turbine engines and propeller rely on the atmosphere to provide air as the working fluid for propulsion and oxygen in the air as oxidizer for combustion. The thrust equation shown above works for both liquid and solid rockets. There is also an efficiency parameter called the specific impulse, which works for both types of rockets and greatly simplifies the performance analysis for rockets. The details of how to mix and burn the fuel and oxidizer without blowing out of the fuel are very complex. The major components of a rocket engine are therefore the combustion chamber, igniter, propellant feed system, valves, regulators, the propellant tanks, and the rocket engine nozzle. In terms of feeding propellant to the combustion chamber, liquid propellant engines are either pressure fed or pump fed, and pump fed works in either a gas generator cycle, a staged combustion cycle, or an expander cycle. A liquid rocket engines can be tested prior to use, whereas for a solid rocket motor, a rigorous quality management must be applied during manufacture to ensure high reliability. A liquid rocket engine can also usually be reused for several flights, as in the Space Shuttle and Falcon 9 series rockets. Although reuse of solid rocket motors was also effective demonstrated during the Space Shuttle programs. Liquid propellant can leak, especially hydrogen, possibly leading to the formation of an explosive mixture. Turbo pumps to pump liquid propellants are complex to design and can suffer serious failure modes such as overspeeding if the run dry or shedding fragments at high speed if metal particulate from the manufacturing process enter the pump. Cryogenic propellants such as liquid oxygen freeze atmospheric water vapor into ice. This can damage or block seals and valves and can cause leaks and other failures. Avoiding this problem often requires lengthy chill down procedures which attempt to remove as much of the vapor from the system as possible. Ice can also form on the outside of the tank and later fall and damage the vehicle. External foam insulation can cause issues as shown by the Space Shuttle Columbia disaster. Non-cryogenic propellant do not cause such problem. Non-storable liquid rockets require considerable preparation immediately before launch. This makes them less practical than solid rocket for most weapon systems. Thank you.